Welcome to this, our 15th discussion. We are going to do a quick review of complex power, the ideal transformer, and three-phase. Then we're going to introduce some new things, the one-line diagram, which will save you a lot of trouble when you're working on three-phase systems, and we'll explore three-phase transformers. In our previous discussions, we said that complex power is additive. As an example, let's take a look at a small factory with three complex loads. We'll let that first load be a 5 kilowatt heater, which means that the heater is pure resistive. We'll let the second load be a collection of machines, which together provide 50 kW with a power factor that's equal to 0.7. And finally, we'll add 20 kVA of power factor correction capacitors. Your opening move for this problem is to present the power triangle for each load. The first one is very easy. Since it's just a resistor, this will be 5 kilowatts. Again, all real at an angle of 0 degrees. The second one takes a little more work. We're told that this has 50 kW of real power, and we're told the power factor is 0.7. Cosine theta is equal to the power factor, which in this case is described as 0.7. Theta is equal to inverse cosine of 0.7, which gives us an angle of 45.6 degrees. We can write that here. We also know that the power factor is a ratio. It's a ratio of the real power to the apparent power. In this case, if we manipulate the equation and we solve for the apparent power is equal to the real power divided by the power factor, which is 50 kW divided by 0.7. 50 divided by 0.7 gives us 71.4 kVA. We can write that here as 71.4 kVA. And finally, we need to solve for the VARs. So volts, amps, reactive. We would say Q is equal to, by the way, remember this is power as P, this is VARs as Q, and this is apparent power as S. Q is equal to the root of 71.4 squared minus 50 squared. So 71.4 squared minus 50 squared equals, and you take the square root of the answer, gives you about 51 kVAR. So 51 up there. That takes care of load 2. Now we can look at load 3. This one again is very simple. It's simply a straight line pointing down, and that is negative 20 kVA. Actually, it's not kVA, it's negative 20 kVAR. Now that we have our three power triangles, we look back and we remember that power is additive, so we can calculate the factory's total complex power as the sum of the three power triangles. We can add up the real pieces first, so that's 5, got that one, plus 50, there's that, plus 0, because there is no real component on the capacitor, So that brings us to the reactive pieces. So this guy here is plus J51 minus J20, and that's all volt amps. When we put this all together, we end up with 55 plus J31 kVA. Looks like we lost that up here. Let's go fix that. kVA. The complete power triangle looks like this. We have 55 kW and 31 kbars. If you want, you can use your calculator to solve for the rest of that triangle. So 55 plus 31J equals, and then shift it over to polar form. That tells us that it is 63.1 kVA at an angle of 29.4 degrees. The power factor for the entire factory is cosine theta, which in this case is cosine of 29.4. So cosine 29.4 gives us a total factory power factor of 87%. What would happen if we went back and turned off the power factor correction capacitors? That would mean we took out this piece here. We removed the capacitors which were providing negative 20 kVAR. Our new S total becomes 55 plus J51 kVA. The power triangle looks like this. We have the same 55 kW here. The angle is now different though. So this is 51 kVAR. Put that into the calculator. That's 55 plus 51J equals, and then shift to polar form to solve the rest of the triangle. Gives us 75 kVA at an angle of 42.8, which is quite a change. So our power factor is now 73.4%. Let's see what that does to the current for our factory. You remember we had an equation that told us this, that the complex power is equal to the complex conjugate multiplied by the voltage vector. So that's the tool that we're going to use now to find the current. We're also going to assume that our factory had a 277 volt feeder. With the capacitor, the complex conjugate of the current is equal to the complex power over the voltage, which was 63.1 kVA at a phase angle of 29.4 over 277. That is 63100 at a phase angle of 29.4 divided by 277. Gives us a current. Actually, it's the complex conjugate of the current of 228 at a phase angle of 29.4 degrees. And now when we calculate the current is equal to 228 at a phase angle of negative 29.4. Again, what we did in that step is we got rid of the complex conjugate. Without the capacitor, the complex conjugate of the current is S, so that's 75 kVA at a phase angle of 42.8 over the voltage. So the complex conjugate of the current is 75000 at a phase angle of 42.8 divided by 277. gives us 270 amps at a phase angle of 42.8 degrees. And then we need to get rid of that complex conjugate, so the current without the capacitor is 270 amps at a phase angle of negative 42.8 degrees. So something to notice, the real power is the same in both circuits. In both systems, it's 55 kilowatts. However, the current without the capacitor is 42 amps higher. And that's an unexpected result. If we remove a component, right, we removed the power factor correction capacitors, and our current increased by 42 amps. This is what a search for power factor correction capacitors looks like. You'll find the capacitors themselves, which are shown in these pictures here, and you'll often find them in enclosures such as this. These capacitors will be put into the circuit as necessary to correct for the highly inductive loads that you often find associated with motors. In this example, we were able to take a poor power factor of 73% and improve it to 87%, which can improve system efficiency and ultimately save money. Before we start our three-phase discussion, let's work a quick transformer problem related to complex power. In this example, we have a 30 kilowatt load with a power factor of 0.8 inductive. It operates from a 277 volt system. We'll assume that is an angle of 0 degrees. It is fed by a 15-to-1 step down transformer. There's an unknown current and an unknown voltage. From your note card, number of turns in the primary over number of turns in the secondary is equal to the voltage in the primary, and that's a phasor voltage, over the voltage in the secondary. And then the current is upside down, so that's the current in the secondary over the current vector in the primary. Also, the complex power going in on the primary will yield the same output power on the secondary. These statements are true for an ideal transformer. We can start this with our power equation. So complex power is the complex conjugate of current by a voltage vector. In this case, we're told that this is a 30 kW load. That's real power with a power factor of 0.8. So theta, or correction, cosine of theta is equal to 0.8, which gives us a theta inverse cosine of 0.8. So it gives us 36.9 degrees. Power factor is equal to the ratio of real power to apparent power. 0.8 is equal to 30 kW over S. Solving for S, that's 30 divided by 0.8 gives us 37.5, and that's kVA. Finally, we can say that S, the vector, is 37.5 kVA at a phase angle of 36.9 degrees. Which brings us back to our original problem. What is this current right here? The complex conjugate of that current is equal to S, which we just calculated, So that's 37.5 K at a phase angle of 36.9 degrees, all over 277. So that is equal to 37500 at a phase angle of 36.9 divided by 277. And polar form, please. So that gives us a complex conjugate of 135 amps at a phase angle of 36.9 degrees, which works out to a current of 135 amps at a phase angle of negative 36.9 degrees. Once again, do not forget that complex conjugate piece. You must remove it or your angles will come out wrong. So that's what we have here. This current is 135 amps at a phase angle of negative 36.9 degrees. And what we want is this current here and this voltage. This is a step-down transformer, which means the voltage here is stepped down to give you this voltage. That's another way of saying this piece right here. The voltage is reduced by a factor of 15 to give you 277. So if we work that backwards, we would say 277 times 15 gives us our voltage. In this case, 4160. The current is the opposite. So when we have 135 on the low voltage side, we can expect that to be reduced on the high voltage side. So for the current, it's 135 divided by 15, which gives us this current here as 9 amps at a phase angle of negative 36.9 degrees. I'll leave it up to you to work those numbers through these formulas right here. Our next stop is three-phase. We did address this briefly in a previous lecture. We talked about a Y connection and we talked about a delta connection. The Y connection takes this form. So let there be a resistive inductive load. This is the A line, the neutral, B, and C. And this is called the Y, otherwise known as a star. The main thing to identify this type of connection is the central node. All points share it. There is an alternative way to draw this, which might be a little simpler. Phase A, phase B, phase C, and neutral. You'll notice that this central point is still there because all of those points share that common node. Okay, that was the Y. Again, two different ways of showing it. Now we move to the delta. With phase connections of A, B, and C. The alternative way to draw a delta looks like this. Be careful. When you do this, you have to make a loop. Here's what I mean by loop. With this configuration, it's pretty easy to see. We just go in a circle. With this one, the circle is still there. You just have to look for it. And that is one of the defining characteristics of a delta. We can talk about a loop. When we explore three-phase systems, the question of where do you measure always comes up. As an example, consider this three-phase generator. Phase A, Here's our neutral, phase B, and phase C. You would recognize this as a Y configuration. This generator might produce 277 volts at a phase angle of 0 degrees. We'll let this one be 277 volts at a phase angle of negative 120 degrees. And this third one as 277 volts at a phase angle of negative 240 degrees. Or if we go around the other direction, we say 277 volts at an angle of 120 degrees. You could measure a single phase. You could also measure line to line. In a Y system, this piece here is what we call a phase, which is the same as saying a measurement going from volts line to neutral. Okay, so in a Y configuration, to measure a phase is the same thing as saying measure line to neutral. If you're going to measure phase to phase, that looks like this. So voltage phase to phase, or voltage line to line. And obviously these are not the same thing. You may recall an equation, voltage line to neutral is voltage line to line divided by square root of 3. Or if you rearrange that, voltage line to line is equal to root 3 voltage line to neutral. In this particular system, we have 277 volts. That is a phase voltage, which is to say it's a line to neutral. So volts line to line is equal to root 3 of 277. So that works out to 480 volts. So this meter reads 277 volts, again, line to neutral, whereas this one measures 480 volts because it's going from line to line. Let's take a look and see where this comes from. We'll redraw part of that previous circuit. We'll put a load out here. We said this was 277 volts at a phase angle of 0 degrees, and this one was 277 volts at a phase angle of negative 120. We'll let this be A and B, and we're curious, what is the voltage out here? What is voltage A to B? Using Kirchhoff's voltage law, we walk the loop. So we start here and we walk that way. The first thing we encounter is a positive terminal. So we record that as 277 volts, angle negative 120. Then we walk into this terminal. So that's that's minus 277 volts, angle 0 degrees, plus voltage A to B is equal to 0. If we rearrange this, we say the voltage A to B is 277 minus 277 angle negative 120. And push that through your calculator as 277 minus 277 at a phase angle of negative 120. And put it into polar form. There you are, 480 volts at an angle of 30 degrees. So this meter here reads 480, and we already established that there was a root 3 relationship there. This is a good time to start our talk about three-phase transformers, but before we do, I wanted to mention the one-line diagram, as it will make our discussion much easier. For example, in our previous problem, we presented a factory. And if you were to make a one-line drawing of that factory, it would look like this. So we have a transformer. We have our heater. We had those motors. And then we had our power factor correction capacitors. Everything is shown as one single wire. Okay, we didn't draw them all in. In reality, our factory would look more like this. Here are the three phases, plus a neutral, plus a safety ground. So A, B, C, neutral, and ground. We'll assume the heaters are in a Y configuration. Probably not in real life, but we'll show them that way anyway. We'll let this be phase A. Here's our connection to phase B and our connection to phase C. And we may as well add the neutral in there as well. Okay, so there's our heater. Next we have our motors. So we'll show that as phase A, phase B, and phase C. There's A, B, and C. We may as well connect the safety ground to the motor. And finally, we have our power factor correction capacitors. We'll show those in a delta configuration, connected to phase A, phase B, and phase C. So that is a representation of the complete factory. I think you'll agree that this one-line drawing makes things a little bit simpler and easier to understand. What we're going to do now is focus in on this feeder transformer. We're going to talk about three-phase transformer connections. There are four general configurations that we can use. We could connect delta to delta. You could connect a delta to a Y to a delta, and a Y to a Y. This configuration, where we go from a delta to a Y, is fairly common. So that's a 5-wire system, 3 phases, neutral plus ground. And that's the one we find in our lab when we talk about a 208/120 system. 208 line to line, 120 line to neutral. I should mention, with respect to these one-line drawings, you'll also see transformers written like this. We'll let this be a delta to a Y. For example, you could have 4160 in, and you could have 480 in a Y configuration out. This is what it would look like with all of the wires drawn in. So we'll let this be our 4160. We're going to make a delta here, and we'll let this be our 4-wire Y connection leaving. So we'll draw the transformers here. And then we'll connect them up. So this is phase A, phase B, phase C, A, B, C, and neutral. So we're connecting this transformer. We'll call this T1, T2, T3. So we'll let that one go from A to B. We'll let transformer 2 go from B to C. And then this last one, C to A. Now remember I said that deltas were loops where you could travel around the edge of the loop. Let's see if we've done that. So here is the loop. For the Y configuration, we'll let this drop down to neutral on every single transformer. Then we'll bring this to A, this to B, and this to a C phase. And that completes our connections. We have a delta connected primary going to a Y connected secondary, which is exactly what we have shown here. There are other ways to view these connections, so I'm going to take a moment to sketch that out now. A delta is a loop. So we could connect here, here, and then bring this wire over like this. So if we were to follow that, it's like, well, sure enough, we've made a loop. But now we need to connect it. So the connection to phase A would be there. The connection to phase B would be here. And the connection to phase C would be there. Again, this is identical to before. This is our first transformer. It's connected up A to B. Our second transformer is connected up as B to C. And our third transformer is connected up C to A. Again, starting at C, going through this loop back to A. We can do a similar thing on the Y connection. So often you'll see a Y like so, where the connection is made up here. And then you bring the connections down. So this would go to neutral. This would drop down to A, to B, and to C. If you were to search for three-phase transformers, you would find pictures that look like this. You can see that it's common to wind all three windings onto a single core. For example, here's the primary windings, and then here's the secondary windings. Speaking of windings, the turns ratio very much depends on the configuration that the transformer is used in. For example, if this was your transformer, if you had a 4160 delta going to a 480 Y, what would it look like? Remember that this here is a voltage line to line, and this is another voltage line to line. I think I addressed that before, that if you see a number all by itself, that is an RMS voltage, and it means volts line to line, or phase to phase. The delta connection would look something like this, where we have incoming phase A, phase B, and phase C. The Y connection would look like this. We describe this as a 4160 delta, and this as a 208Y. If we scroll up a bit, you'll see that we've already done part of this problem. If we let this be 4160 delta, and we let this be a 208Y, we can see that this primary of T1 is connected line to line. So that means there's 4160 volts on the primary. On the secondary, it is not connected line to line, rather it's connected line to neutral. So instead of seeing 208, we see 120 volts. So this is a 4160 to 120 volt step down transformer. If we were to sketch that here, we could talk about a voltage as 4160 on this side. We can talk about a voltage across the phase of this transformer as 120. And finally, just for completeness, if we were to measure phase to phase, we would read 208 in this particular system. So the turns ratio is 4160 to 120. And if you solve for that, you see that's 4160 divided by 120 gives us a turns ratio of 34.6 to 1. Or if we went back up here, we would say this is 34.6 to 1. So that is the turns ratio for this particular system. I think that's enough for one day. When you come back, we'll talk more about distribution and the use of transformers.